Good catch. Okay, I better double check to make sure the audio is getting recorded. Yes, it is. Okay, cool. All right, so question number 1 is using the correct architecture, if a program needs to increment the value of a register, say register A, what instructions is or are needed? Okay, it's not correct, it's supposed to be current. Okay, so using the current architecture, the one that you did your homework assignments on, if I need to add 1, okay, which is increment, if I need to add 1 to the value of a single register, say register A, what do I need to do? You guys know the answer already, okay? Because it involves, a certain instruction to get the 1 into something, because the ALU can only process things coming from the register bank, okay? So you need to get that 1 into something first. So the answer to the first question is fairly easy. And then in the second question is, with your chosen instruction sequence, what is affected other than the register A that we want to increment? In other words, I'm asking you about the side effects of those instructions. What else is being changed? I just want register A to increment. I don't want anything else to be changed. But in order to get it done using this architecture, something else is going to get changed. Yep.
When you say instructions, do you mean like the mnemonics?
The mnemonics.
Okay.
Yep. So you don't have to spell the actual opcode, you just use the mnemonics. Okay. So question number 2 is kind of important because we usually don't think about it. Okay. We just want to add 1 to register A, but in the process of doing that, what else is modified? Okay. One part of this answer is kind of obvious, but the other part is less obvious. Okay, so I will disclose the answer on Thursday. Question number 3, which is related to question number 2, reviewing the processor architecture right now, okay, what you have at this point, how would you propose to connect the data port of RAM to in2 of the ALU? This is to allow instructions to directly use RAM content as the second operand of arithmetic instructions. So when you're adding, we want one part of the add to come straight from memory instead of coming from another register. Your suggested change should not affect the microcode of instructions already implemented. So the existing add instruction should not be impacted by this change. The existing LDI instruction should not be impacted, nor to introduce additional control lines. So I don't want to have to change the width of the data port of the ROM, with the microcode. So with only the existing control lines, how do you get this done? So that's question number 3. Question number 4 is based on question number 3, borrowing the idea from the, well, not yet. Borrowing the idea from the LDI instruction and utilizing the answer from question number 3 suggests how you would microcode and add immediate instruction so it has the following effect. So this is the mnemonic ADDI for add with immediate. X is denoting a particular register, and then I is the constant that you are adding to X. So this is using about the same kind of notation as LDI. And in terms of the pseudocode in C, it is just adding whatever the program counter is pointing to register X, and then we also want to auto increment the program counter afterwards. Okay. In other words, this is really similar to some of the instructions that is already implemented at this point, but it's going to utilize something from question number 3. Okay. You can assume the base code of the add-I instruction is 30, and the bit code is 0011. That's how we got the 3, and then 00XX is how we got the 0, and XX together specifies which register we're dealing with. So it is similar to the homework assignment, but with a little twist of you also need to make some architectural change to the processor itself. Okay. Now this is harder than the actual question in the exam because you have a little bit more time right now. So I want you to kind of spend some time to kind of investigate how to get this done. By doing that, you are studying. Okay, so these questions are not really just as practice exams. This is actually helping you study because it's forcing you to look into the computer architecture of the toy processor and then figure out, okay, how do we get this done? So question number 5 is the only one that is not related to the other 4 questions. It is the floating point questions. Okay, But instead of just asking you to give me the final answer, I'm going to give you steps. So to represent the value 0.625 in double precision floating point number representation, derive your answer step by step so that the finished answer is in the form of a hexadecimal number representing a binary bit pattern. Are there questions about what I'm asking for? Is the question itself clear enough? Okay, all right. So I break this up into multiple steps. In step 1, I just want you to separate the components of 0.625. Okay, what is the base 10 mantissa? What is the base 10 exponent as presented? So in this case, the mantissa itself is really just 0.625, and then the base 10 exponent is 0 because I'm not using the scientific notation. Step 2. You have to give me the sign, the base 10 mantissa, as an unsigned integer. So in order to turn 0.625 into an unsigned integer, what do?
Multiply by 10 couple times.
Yep, you multiply this by 10 to the power of 3. Okay? But as a result of this, you have to adjust the base 10 exponent so that the value that you're representing does not change. Is that okay? In other words, I'm just guiding you through the process that your program had to do. And it's open book, open notes, which means you can bring the source code of your homework assignment to the test, or my code. Okay? It's open book, open notes. And then the next one is the sign, the mantissa being converted in the process, and the base 10 exponent is being changed in the direction of 0. In other words, if the base 10 exponent was positive to begin with, you're trying to decrement it each one step at a time. If it is negative to begin with, you want to increment it one step at a time. But in the process of doing that, you will have to adjust the base 2 exponent in order to account for the base 10 exponent change, which is what your program had to do too. Okay, so you just have to kind of do this step by step. I'm not going to give you values that are really hard to work on. There are some additional examples down here. And then step 4 is you have a sign, you have a base 2 mantissa as an unsigned integer. You have a base 10 exponent that is now 0, which means it is no longer useful. And then you have a base 2 exponent in step 4. In step 5, you have to do the implicit shift because your mantissa from step 4 is an unsigned integer, which is really large. So I want it to become 1 point blah, 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 blah. So you have to do the shift of the binary point all the way to the right position. But to do that, you have to adjust the base 2 exponent to deal with that change of the decimal point or the binary point. And then step 6 is just to encode everything in IEEE double precision format. And the only one that is kind of tricky is the exponent is actually offset by 1023. So I think it's doable, okay? Because I have some more examples. So once you're done with 0.625 and you say, oh, that's too easy, you can try these two. You can try these two values. 1.28 E2 is what? 128. And why do you think I chose 128? Yep, it's easy. Okay, so that one is supposed to be pretty easy because it's just a power of 2 itself. The other one looks kind of ugly because it is negative 7.8125 times 10 to the power of negative 2. But if you punch in that number, it can be expressed as something over a power of 2. So you just have to kind of figure it out. Okay. It's not that hard, okay? Because the first thing you do is you turn it into 78125 with some exponent of 10 to adjust for that change, and then you just go through the conversion process. And you will see that in the conversion process, it's like, oh, all the divisions will work out exactly. Okay. So is that okay so far with the practice exam? So I'm not going to go over the answer to the practice exam today. I will do that on Thursday. Your actual exam is on the Tuesday right after spring break. Okay, because I'm spacing out the exams for 310 and 440. I don't want those to be on the same day. But on the final day, I have no way to adjust that anymore. Okay. All right. So now we go back to the homework assignment. Okay, so let's go back to the homework assignment. Implementing microcode of a new instruction. fine. All right, so what is the most difficult part of this homework assignment? There are many pieces, right? There are a lot of pieces to this homework assignment. So it's really part of the intention of this homework assignment is to expose you to all the different pieces. So I think I drew this drew this picture last time already, but it doesn't hurt to do it one more time. So we have at the center of everything is the logicsim file that we know as processor WDPC with direct program counter change. So, and then with that simulating the processor, we have, so this thing has a RAM component to store the actual program in opcodes. It also has a ROM component to store the microcode slices. So these two components need to have some kind of content in order for a program to run. To specify the content in RAM, you are more than welcome to try to hand assemble your program using the binary code and whatnot. It's doable. It's just a lot. It's really tedious. It's just a lot of work. So what you can do with this step here is to make use of the assembler as a spreadsheet. You put in your mnemonic program. You go through the assembler, get the file out of it, load it into RAM, and you're good. The ROM, on the other hand, is, you can also hand code it, by the way. Okay, you do not have to use my programs to figure out the slices, but the programs make it easier. Okay, because you don't have to deal with all the bit shifting and all the bit OR. It is already done for you. So it is all.rom that you need to put into the ROM, but all.rom is really just a concatenation of the output of the individual programs, starting with no-op.c, then we have halt.c, LDI.c, and so on. So you have to add your own files, which are jmpi.c, joi.c, and there are 5 or 6 additional files that you have to include in order to generate the microcode slices of all the instructions. Are we still doing okay so far with this entire 2 chain? Okay. So let me go get the homework assignment done first, which I have most of the pieces already in my processor subfolder. Go to opcodes. Okay, so I think one of the hardest portion of this program or of this homework assignment is to figure out what each thing in the slide is representing. Okay. And that part has to do with reading the source code, because that's why the source code is available to you, which is ucode.c. So you have to read ucode.c to figure out, okay, what are those individual pieces doing. So you look at ucode.c, and it has a bit field array. The bit field array called microcode has exactly 18 fields, which is the number of items in slices. And these are already named like that, okay? And these correspond to the names in the circuit diagram itself. So what you need to do is to copy and paste, okay? Just copy what you think is the closest to the instruction that you want to implement. So I'm going to copy JMP to jmpi.c because I think that's the closest instruction. So I look at jmpi.c and I know I need to make some changes. So the first thing we need to do is to figure out, okay, what is the actual opcode? Okay, what is the actual binary bit pattern of JMPI? That one we can figure out using one of the items in the shared drive. So we go to apps.losreals, sign in as me. And the opcode is described in opcode table. So according to this, it is JMPI is a 4.0. So you go back to this code here, and once you read the source code of write slice, you will see that the second parameter is what is controlling the opcode. So this has to be changed to 4.0 because this controls where in the ROM the slices will be placed. So that's why you have to make sure that these two get changed so that the slices will get to the right place in the ROM of the microcode. And then these two parameters basically specify, do we use any XX register? Do we use any YY register? If so, how many bits do we have to shift to get to those two particular bits? So in this case, since this is copied from the JMP instruction, it does make use of XX. And this 2 is basically specifying XX is 2 bits from the least significant bit. So it will be bit 3, it will be bit 2 and bit 3 of the byte. So that's what the 2 is representing. If I do not have a YY register, we just use the constant of no YY. But because now we're dealing with JMPI, does JMPI use any register? So we just say that it does not use register X either. So we can specify no XX right here. There we go. Okay, so that accounts for these 2 parameters. The last parameter is really just letting you specify which slice I'll be talking about, because each instruction can have up to 16 individual microcode slices. So this one just basically say, okay, what you have in the slices, which slice are we talking about? You can specify things out of order if you want to, but we just want to kind of keep things in order. In other words, if you change this program so that it specifies slice 1 first and then it specifies slice 0, it'll work just as well. Okay, there's no difference between this program versus the one before, which is like that. Are we doing okay so far with the calling of write slice? Okay, so the most difficult part, or the most tedious part, I would say, is to figure out what numbers to put into these individual elements of the array slices. So to get this part done, you probably will need 3 things to work together, which is really hard because I'm only running in XGA resolution here. With my 4K monitor at home, it will be pretty easy. Except I'll be smelling the monitor because my eyes are no longer that good. I forgot that when I ordered the 4K monitor. That my eyes is not as good as they were when I was in my 20s. So I will still do it, okay? I'll still go ahead and open up all the documents because that's what you need to get this done. So we'll go open up Logisim first. And then we'll specify the processor architecture. Okay, so we have the processor architecture. I'm going to zoom out just a little bit so that we can kind of get a more overview sight of what we're dealing with here. So what we want to do is we want the data bus coming out of RAM, and the nice thing is you can click on the wire and it will get thickened or highlighted, and you can see where it goes. And you can see right away that it goes into this mux, which is pretty close to the PC, the program counter already. Okay, so you go like, okay, so we are only 2 steps away from the program counter. We have to handle how to get from here to here, and then how to get from here to here. Is that okay? So in order to go from here to here, we have to specify the output of this mux is coming from input 0. And to specify, no, this is input 1, sorry, this is input 1. So in order to specify input 1 becomes the output of this mux, we need a 1 on this wire, right? So how do we get a 1 on this wire? This is an AND gate, so we need PC mux to be a 1. We also need RO0EN to be a 0. Okay. RO0EN needs to be a 0, so we switch back to the code, the source code. And in order to figure out which item here is corresponding to RO0EN, we can look into ucode.c because that one has a string describing each item. So you just look through this thing and go like, oh, okay, just found it. Okay, this is the item. So you have to do some counting. Okay, that part is not exactly avoidable, so it's kind of inevitable. You can turn on line number so you can make the counting easier. So this one is on line 19, and we started on line 8. So we are talking about, is it the 12th item? Calling the first one the first item. This is the 12th item, right? So let me just count by 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 12. It should be 12. Yep. Okay. So then you switch back to the other document, the program that you are actually writing, and then you have to say this is the first item, and you just have to kind of move to the right hand side to the 12th item. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is the 12th item. You need that to be a 0. And you also want this one to be a 0 here because we are not using any XX. So where we find XX should be a 0. But we are not done yet, okay? Because in order for the data bus to be meaningful, okay, we have to see, okay, where's the other end? This is the part that is reading, okay? But where's the other end? The other end is right here, which basically means that you have to make sure that the RAM module is selected, okay? And 2, you have to be specifying a read operation, which means RAM cell has to be a 1, RAM load also has to be a 1. So you go back to the program, okay? And in this case, you want to look, once again, look into ucode.c because it has all the names, right? So that's kind of easy to figure out. Lucky for us, RAM load and RAM cell are the last few items of this entire list. So the second to the last item is selection, and then the third to the last item is load. So we switch back to the program we are going to modify, and then we just specify that these two, they need to be 1s. And I think PC mux being 7 should work. So let me double check on the circuit diagram here. When PC mux is a 7, okay, because this is PC mux, it's even commented here. Okay, if it is 7, we are putting a 1, we are selecting a 1 to become PC mux, which is what we want because we want PC mux to be a 1. In that case, whether it's incrementing or not doesn't really matter because that's not the path that we are choosing to update the program counter. So that part does not really matter. So I think this should do it. Is that what you got in your homework assignment? Yeah. Okay, cool. All right. So we'll just say that this is the 1, and then we can change the makefile accordingly. And we already got this one added, but I don't want to deal with JLI just yet. I just want to add JMPI, jump immediate, into this list. And we got the rule already set up here as well. So we just say make. And now we have all.rom. Now to you guys, especially those who are using Windows for Logisim, but using the Power Server to do the rest, you have to use WinSCV to copy files around a few times, okay, which is kind of tedious, but not, it's not too bad. So now we can go back here, and you might need to turn off simulation to update the ROM. I'm not sure whether that's the case or not. So you say load image, and then we go to the Opcodes subfolder, go to all.rom. Now it is updated. You can always double check too, because you can go to edit content and go to 400 and see whether it has any content. So it has got 2 locations with content in it already. So I think we got it. Okay, so the next step is to test it. Now it's sort of optional and sort of not optional to test whether your microcode is right or not. Because if you just miss 1 bit, okay, it may not work. So if it doesn't cost you too much time, it is worth it to test it, okay? So if you want to test this particular program, then you want to write a simple program in the spreadsheet. So let me go to the spreadsheet, which is called assembler, and just write a program to test the JMPI instruction. So we'll go ahead and specify a label, okay? Now, if you really want to test it, you want to kind of test it with a non-zero location, because a 0 location also maps to no op. Okay, so if you implement your instruction incorrectly, it may still seem to work, but it's not. So it's probably a good idea to put a no op instruction here, but your label is at location 1, and then you can just specify another no op here, JMPI to L1, and get rid of the other non-essential instructions. So now we have an infinite loop. It should go back to this particular no-op instruction, go to the jump, go back to the no-op instruction, and so on. And then we go to the output, the RAM file. With this one, you can just hand enter everything, 00004001, If the program gets more complicated, it is probably a good idea to use a RAM file. But in this case, it's not too bad. We'll just go ahead and hand enter the whole thing. And before that, we have to reset the processor just to make sure that we start fresh here. So we have 0, 0. Oh, we need to select that one. Nope, we need to use that. 0, 0, and then we have a 4, 0, and a 0, 1 here. The first time you do this, I would suggest you to use just single clocking. Okay, so I'm single clocking. It's now executing the second no-op instruction. Now it's reading the third instruction, and now it's grabbing the 0, 1 to be the location to branch to. So this is where I would just kind of be more careful and kind of single step, but also keep an eye on the program counter and also the pathways of the program counter to make sure it's right. So right now we can see that in the microcode portion, we're already on the first slice of the microcode, and we want to double check that all the lines are correct. In other words, we want to make sure that the RAM module is selected, and we are specifying a read operation, so that's good. We want to look at the program counter, making sure that the enable of the program counter is enabled. We want to make sure that the selection of this mux is a 1, so that we are selecting the data output of the RAM module, and we can click on that wire and see that it is in fact specifying 0, 1. And then when we clock it one more time, you can see the program counter is updated to a 0, 1, and in the next instruction, we should continue execution at 0, 1. So so this gives me sufficient evidence that this instruction is working as expected. Okay, so you do the same thing with the conditional branch instructions, except those are a little bit more nasty because you have to specify that the program counter does increment, okay, when you're not branching. So that part gets a little bit more complicated because in order to specify that you are in fact incrementing the counter, you want this wire to be a 1. But if you want this wire to be a 1, you need to make sure that this OR gate does not get 2 zeros as the input. 1 is going to be a 0, okay, because PC-Inc is going to be a 0 because PC-Inc is the flag itself. So whatever flag you choose is going to be one of these 5 wires, okay? This is the carry flag, this is the 0 flag, this is the sign flag, overflow, and this is the L flag. So whatever these flags are is going to become your PC-Inc. So that's not going to be able to add 1 to your program counter. But fortunately, the other thing that you also have to specify is the address mux, because that's how you connect the program counter to the address line of the RAM module, which is what you need to do too, because you might be grabbing that next byte to specify the next location. So it just so happens that if you do that part of the instruction right, it would just increment. So that means you can do exactly the same change that I did with JMPI instruction, but you would use JC, JZ, JO, and JL as the basis of the JCI, JZI instructions. But do exactly the same changes and they should work. But to test the conditional branch instructions is a little bit more cumbersome. Okay, we talked about that last time. In fact, before I changed the program in the assembler, that was the program to test whether it branches or not. So that's something that you have to do. So are we doing it okay so far with the assignment? All right. So the sample questions for the test is related to what we just did, okay? Because we're trying to implement a new instruction, so we are trying to draw a new connection between the data line from the RAM, okay? So we want to highlight this first, okay? And then we want to somehow connect this highlighted line to input 2 of the ALU, okay? So somehow we have to connect this line to the input 2 of the ALU. So that means somehow you have to be able to control what goes into input 2. It can be the current line. It can also be this thicker highlighted line. Yep.
For the exam, are you expecting us to reference this processor design or the original processor design that doesn't cut the additional buttons?
It is going to reference this particular design.
This time.
Yep. Yep.
So let's say if we wanted to add our own opcode, like not one you provide, like add immediate, we literally just do the same thing, but then we just have to hard code it into the RAM because the assembler doesn't know.
Well, I can make the assembler take it. It won't be too much work.
But like if we didn't know how to make the assembler take it, we could just.
Yeah, you can just hand assemble it. Because the add instruction is 0011 and then the other part is 00XX. So that means if you want to implement, if you want to assemble, add I with say register C and I don't know 50 in as a base 10 number. Okay. So if this is the instruction you put into the assembler, the output of this particular mnemonic should then be a 3 in hexadecimal, should be a 3 because of this 3 here. And then register C is 2, which is 10. So you have 3, 2 in hexadecimal as the first byte. Does that make any sense?
So you say that one time C is, oh, because it's address.
Because the actual bit pattern for the opcode itself is 0011, and then XX is specifying register C, which means we need a 10 here. This is 3, this is 2, so that's why 3, 2 in hexadecimal specifies the first byte of this particular instruction. And then you need 50 as a second byte. 50 as a decimal number is in hexadecimal also 3, 2. That's coincidental, okay? I didn't plan out this way, okay? Because it's 3 times 16 plus 2, which is 50, okay? So it just so happens to be 3, 2, 3, 2, okay? But the effect of this instruction will be adding 50 in base 10 to whatever C already has.
And so, what would you put in the RAM for the 3, 2?
Just 3, 2, 3, 2.
Oh, 3, 2.
But in order to test whether it works or not, you might want to put some values into C first.
Is that the RAM or the ROM?
Into RAM. So your job is to specify what goes into the ROM to get this done, and also what changes to the architecture do you need to do in order to get this to work.
And where would the result? Where would the result be stored?
Say that one more time.
The result you just stored in the register?
The result is stored in the register because in the description of the practice exam, let me go back to the practice exam first. Is it this one? Yep. Okay. So in the practice exam, the effect is a x plus equal to, which means the result is stored back into one of the operands. Okay. So is that answering your question?
No, I'm still kind of confused. Because I thought so it's, wait, so for the RAM, because I thought it was like a 2-bit hexadecimal location.
Each location is a byte, which is 2 hexadecimal digits. So the first byte for this instruction is going to be a 32 in hexadecimal, but the second byte turns out to be a 32 as well, because 50 in base 10 is 32 in hexadecimal. It just so happens to be like that. I didn't plan it out. It's just completely coincidental. Is that okay? All right. So at this point, I'm going to change my assembler to make sure that it can assemble that instruction. And you guys can take a look at how you can implement a new instruction in this assembler. And then first of all, I have to find it, which is here. Okay. So to add a new instruction, you just have to do some changes to the mnemonic part first. So we have a new instruction called add I. You're trying to edit parts. Do not show this for 5 minutes. Think that might be enough time for me to get this done? Maybe. Okay, maybe. So the actual opcode is a 30. Okay. It does need to specify where to find x. 0 means the first, 1 means second. So this means the bit. Which operand are we dealing with? So this is operand 0. This part you can just copy from LDI because LDI has exactly the same format. So when you look at LDI, which is right here, that's a 0. So we also need to specify where we specify the immediate operand. So this is it's the second thing. And then column F needs to be specified too, because we want to be, this is the syntax. Okay, what can we expect as the first operand? It is register A to D. So we just have to specify exactly the same thing in parentheses A-D, which is actually a part of the regular expression to recognize a register. So then the last one, nope, that's it, I think. Oh, we have to specify a 0 here because it is specifying where we find register X. So we will do that. Put a 0 here. And the comment is here. Okay, if you go to the little triangle at the upper right-hand corner, it shows you the comment of a particular thing. So this is XX, this is YY, and I think that should be it. So now we should recognize that instruction. We'll test it. So we'll go to the other tab, go to source, and just kind of give it that instruction to assemble. It doesn't even have to make sense in this program as far as the flow of the program is concerned. So we have add I, register C, and we'll do exactly the same thing, 50, because we already know what opcode should be generated. You can see it doesn't generate any error messages here, which means it is recognizing it. But the question is it really outputting the correct code? So we go to output, and it's generating 3232, which are the correct code. So the assembler is now recognizing add I as an instruction. It will generate the actual opcode, but your job is much more difficult because your job is to change the architecture first so that you can have a switchable path to connect the data bus to input 2 of the ALU, and without impacting the rest of the instructions. Okay? And once you have that pathway set up, then you have to set up, you have to tell me what will be the microcode specification to get it to work. But I'm suspecting once you programming the pathway correctly, then specifying what bit pattern you have to use will be pretty easy because by design, you already know what to do. Yep.
Okay, I think I get it now. So the first 3-2, that's padded in the ROM. Is that right?
You mean this 3-2?
Yeah,
This 3-2 is corresponding to the opcode of add immediate. And then this 3-2 specifies what are we adding to register C.
Yeah. And then the second one's RAM.
The second one's just representation.
It has the same flavor as an LDI instruction, except we are not just putting whatever the second thing is into the register, we are adding it to the register in this case.
Okay. I'm just confused on what the RAM representation would be. The RAM representation.
The RAM representation.
This 3-2, right?
Okay, so it sounds like that's something we can clarify in the lab. So when you're working on this here, we can clarify that. Okay. So are we okay so far in terms of getting started with the practice questions? Yes? Okay, all right. All right, so we are done with the practice questions. We got about half an hour left. So what we'll do today is to talk about the stack, okay, and how subroutines are implemented. Is that okay? So we'll do that, step by step. We'll start with a C program to illustrate what is a subroutine and how it is done. And we'll start with something that's relatively simple, and then we'll progressively get to something that's more and more difficult. Okay? So I'll just go to the temp folder to make these sample programs. So I'll just call this one sub1, which is the first program to deal with subroutines. And in this particular subroutine, okay, we'll just return void with function f with no parameters, and then in main, we'll just call that. And we'll call it one more time. And then we'll return 0, just like that. That's my entire program. Pretty easy, right? Okay. But there are questions that I want to ask. Okay, when you run a program like this, the question is, I don't have a problem with going from main to F. Okay, that's pretty easy. because I just spelled out where I want to go. The question is, how does F, when I'm in subroutine F, how does it know where to get back to into main? That's the question. Does that make any sense? Okay? Because you cannot just say that, oh, we need to go back to the second line in main. No, because it depends on where we call the subroutine. We want to return to whatever is right after the call. Does that make any sense? Okay. All right, so what we'll do is, I'm not 100% sure whether the 64-bit instruction set is what I want to use, because I think it might do something funky to the program, but we'll give it a try. Or we can do this in assembly code. Let's do it in assembly code. Okay. All right, so we're looking at this program here. It has no variables whatsoever. We're just dealing with control flow in this case. Can we do this using the toy architecture that we already have? Okay, I would say that we can, okay? It's a little tedious, but we can do it, okay? Then the next question is, in addition to all the concepts that we have already talked about, do we need anything in addition? The answer is yes. There's one little thing that we have not really talked about that is needed when you're dealing with subroutines. It's called the stack, okay? S-T-A-C-K, which is also known as last in, first out, okay? So what we'll do is I'm going to go back to my notes so I can point out which portion we are talking about. So we have pretty much talked about all of these things already, including control structures. So it is actually in the next section that we start to talk about subroutines. And the first thing it talks about is the stack. Now, these are all written back in the days when I used the Intel architecture. So the concept discussion is still valid, but in terms of the actual opcode, it is not the opcode that we are dealing with. Okay. Can someone tell me what is last in, first out? What does it mean when I say last in, first out?
Last instruction.
Not so much an instruction, it's whatever you want to store, okay? So whatever you want to store, the last thing that you store is the first thing that you're retrieving, okay? In real life, we have examples of last in, first out, and most of the real life examples of last in, first out are unintentional and also not exactly the right way of doing things, okay? So you have a U-Haul truck. U-Haul truck has a granny loop, I think. That's where you can store something, right? So when you're moving, you're going like, okay, I need to keep track of where I'm going, the destination that you're moving to. So you say, okay, I don't want to lose this, and then the first thing you do is you put it right here. The map, the address of where you're going to, your new apartment, you put it here. Then you load up the whole truck, right? And let's say you're moving to UC to Davis, so you put the bicycle all the way back here, and you slam the tailgate shut, okay? Because the whole thing is packed. And then you realize one thing. Oops, where's the map? It's right here. This is the first thing that you put in, right? So how do you get to the first thing that you put into the U-Haul truck, which is by nature a last in, first out? You have to empty out the entire truck, because what is the first thing that will fall out of the truck? Your bike, because it's last in, first out. The last thing that you shove into the truck is the first thing that's going to fall out when you open up the tailgate. Is that okay? So that's a last in, first out, not convenient in this case. Your refrigerator, okay, so this is a side view of your refrigerator. These are the doors, okay? This is the interior of your refrigerator. It is also, unfortunately, by nature, a last in, first out, okay? Because what happens when you consume your food? These racks will get start to empty out, right? So you go to Costco, okay? You buy a lot of stuff, so you dump everything in, and then you consume all the things halfway through, and you go like, oh, we're running out of something. You go to Costco again, you buy something. Unless you are unless you make an effort to make sure this doesn't happen, what happens next? Your new items will now be here, right? And then you consume these items and you buy new items and they will be here as well. So what happens to all the things at the back of your fridge? Yeah, it becomes a little mowed garden, right? with all the colorful stuff, purple, green, and so on. Okay, so it's unfortunately it's not supposed to be a last in first out. If it is a first in first out, would be much better. Okay, so we have an idea of what is last in first out now. And in C and C++, to implement last in first out is relatively easy. Okay, I'll just go ahead and give you an idea of what I mean by relatively easy. So I need to use mousepad. Okay. And this is just an implementation, but it is also pretty close to what we are going to do. So we have an array. Okay, so in this case, I'm just going to use a char array here. We'll call the char array stack. We'll pre-allocate it with a certain number of items, and we'll just, I know you guys don't want to use this, so I'm going to use const here. Const unsigned stack size, and we'll just call that, doesn't really matter, 64. Okay, so we have 64 bytes, on our stack. And here we have stack size, like so. Okay, so we have just allocated the stack. Okay, basically a chunk of memory in RAM is now designated as quote unquote the stack. So now we have to figure out, okay, so how do we access the stack? To access a stack, we have a stack pointer. In this case, because each item on the stack is a char, so the stack pointer is going to be a pointer to a char. Okay, stack pointer, or I'll just use the abbreviation SP for stack pointer. Okay. These are all the constants and the data that we need in order to implement a stack. So now we need to do some primitives. Okay, we need to specify, how do we initialize a stack? So we say initialize stack. And I'm doing some really bad programming practice here. I'm using global variables. So all of these are kind of global. And then we need something to push something onto a stack, which is to store something in a stack. So we will say push, and then we have to specify what item we are pushing on the stack. So we say item to store. And the last thing is we have to be able to pop something from the stack to retrieve an item from the stack. So pop just has a return value. So once again, what initialize stack is going to do is pretty simple. Okay, we just want to initialize the stack pointer. Push is to store an item on the stack. And then pop is to retrieve an item from the stack. Okay. Are there any questions about these three primitives? Only two are really useful. Initialize is only called once. Is that okay? All right. So the first thing is the most confusing part is the initialization is not doing something like this, because most people would say, oh, let's go ahead and start from the beginning of the stack, which makes a lot of sense, okay? Because we like to use things from the beginning, not from the end of something. But in this case, it is from the end, okay? So we want to do something that is kind of awkward, okay? We just say, there are two ways to specify this. You can specify this is the address of the one thing past the end of the entire stack. Or you can say, the other way to say this is to say SP equals to stack plus stack size. We're using pointer arithmetics. So these two statements are exactly the same. You can choose one or the other. But we're initializing the stack pointer to be one past the end of the entire stack, which is kind of odd. Okay. So one thing that we want to do here is to say the stack pointer points to the quote-unquote last item stored on the stack. Okay. Now, because we're initializing, the stack is empty, there's nothing stored. So what we are pointing to is quote unquote the last item stored, which is irrelevant in this case. Okay? Right? So how do we store something? Knowing that the stack pointer points to the last item stored, how do we store another item on the stack? Now, it really helps to kind of get a pictorial representation. So we'll recycle some of this paper here and switch to camera view. Okay. So most people, when we think of a stack, we like to roll a stack from the bottom. But in this class, and all computer architecture class, we look at the stack upside down. Okay, this is high memory, this is low memory, and this is the stack pointer. So when we want to store something to the stack, what we need to do is to say, hey, you know what? Whatever the stack pointer is pointing to, which is this item here, is already used. Do not use it again. So the first thing you need to do is to decrement the stack pointer. So you move the stack pointer to point one location lower than what it used to point to, and then you can say, oh, this is a new location. Let's go ahead and store something here. So this is the new item that you store. So you basically, this is the first step, is to decrement the stack pointer. And then the second thing that you do is to store whatever value you want to store to where the stack pointer is now pointing to. The first step is to allocate the space. The second step is the actual copy. Are we doing okay so far in this in terms of the concept? You allocate and then you store. But since the stack pointer is always pointing to the last thing that you have stored already, you need to move the stack pointer first to allocate that space. Is that okay? All right. Yep.
So you can, if I'm understanding you correctly, you can use pointers to kind of get around the first 10 lines out?
Yes, we are using pointer in an array to do it. Yep.
So why do you point past the end of the?
Because that's the only way to represent an empty stack. Because when your stack is empty, the definition of a stack pointer gets a little bit tricky, right? Because the definition of the stack pointer is it points to the last thing that you store. But when the stack is empty, there's no such thing. So you have to point past the end of the stack. If you point to the very end of the stack that is still a part of the stack, then you're gonna waste that one space, one byte in this case, because you will never use that byte. It has to do with the definition of a stack pointer, always pointing to the last item that you push on the stack. Is that okay?
There's no worry about actually pointing into something that's.
As long as you don't read or store into that location, it doesn't harm anything. Okay? Because you can always just say a pointer is null, but as long as you're not dereferencing a null pointer, it doesn't cause any problems. Okay? So we'll go ahead and go back to the source code, okay, and see how we can implement the push instruction. Okay, the push is really doing exactly the two things that we mentioned earlier. The first one is to allocate. So I'm going to comment here and say allocate one location, and that has to do with decrementing the stack pointer by 1. Okay, SP equals SP minus 1, minus minus SP, SP minus minus, they all do the same thing. Okay, so we allocate the space by moving the stack pointer, but you can move the stack pointer all you want. It doesn't access anything on the stack. Then the second instruction, or the second thing that we have to do, is to store item, which is the parameter, to store at wherever SP points to. So now we say whatever SP points to is item to store. And to be a little bit more safe, you can also make this a const because we are not actually changing anything here. Yep.
Wouldn't you want to check to see that you haven't already filled the stack?
You can check first. Okay, so if you want to check, then you want to perform the check before you even decrement it. So you want to see whether SP is already at stack. If SP is stacked, then you're done. I mean, you cannot store anything anymore. But since we're dealing with regular C, there's really nothing you can do about it, except I guess you can exit the program right here, or you can just say do a planned runtime error here. But there's no way to really recover in the condition when your stack has no space left. But that's a good point. So assuming the stack still has space, this is what you do. So when you're popping or when you're retrieving an item from the stack, can someone remind me again what is the stack pointer pointing to? The last item that we stored, okay? And when we are retrieving items, what are we retrieving? The last item that we stored, because it's last in, first out, okay? So that makes it kind of easy because we can just say return whatever the stack pointer points to, but then we have a problem because you have to adjust the stack pointer. once you retrieve that item, you have to say, oh, this item is no longer on the stack. The item on top of that becomes the last item. Okay, so this one, with this one, the best way to do it is to use a temporary variable first. So I would use a temporary variable to say that that is whatever we want to return. So in the end, we have return TMP. But there's one more thing we have to do before the return, which is to say, oh, that is no longer useful. Let's increase the stack pointer by 1. Does that make any sense? Because whatever we are returning this time is already gone. We are retrieving the item. Yep.
Do you not want to clear that spot in the?
No.
Okay.
Yeah. So with most processor architectures, they do not clear whatever is no longer in use. In other words, you can kind of imagine that you have a book, okay, or a stack of paper, which is your stack. Okay, you have a pile of paper, which is your stack. The stack pointer is a bookmark to indicate anything above this point is in use. Anything below this point is not in use. So when you're deallocating, deallocating a location, you're only moving the stack pointer, moving the bookmark around, but you're not erasing all those pages. So the pages will still have the same content as before. It's just that you use your pointer to basically say, oh, anywhere below this point is not allocated.
Will it will it like replace it when you store something new that's
Yes.
no longer needed, or will
Yes,
it just keep adding?
because okay, so when you look at what we do with a push, the push is going to first allocate a space, and then it's going to override it with whatever new value you want to store. So these two operations are exact opposites of each other. When you look at the decrement to allocate, we are using increment to deallocate. And when you look at the order, okay, we are storing something onto the stack in this case. We are returning something from the stack in this case. But there's also one opposite, which is in this case, we are changing the stack pointer before we dereference. In this case, we are dereferencing the stack pointer first, and then we are changing the stack pointer. So in almost every single aspect, they are opposites of each other. So are we okay so far with these 3 subroutines? One to initialize the stack pointer, one to push items onto the stack to store something on the stack, and then the last one to retrieve something from the stack. So we're good with all those? So let's see how we can implement call and return using stack operations, okay? Maybe, yeah, I think we can do that. So we go back to the program that we saw a little bit earlier, which is this program here. And then we want to convert this program into assembly code. And we'll do it step by step. Okay, so we'll deal with main first. In assembly programming, you don't really have a main program. It just starts execution from location 0, 0. So let me see if I can do this. I want to do a vertical split. There we go. So now we can use the right-hand side to specify the code in assembly code. So we'll do a sub1.asm. I'm just going to give you the random extension here. Okay. So we want to replicate the same thing as in this program here. The location 0 is our main, okay, because this is where we start execution. There's no way you can control the program to start from any other location, because the behavior of resetting the program, resetting the architecture, is to zero out the program counter, and that's why you always start execution from location 0. Is that okay? So the first thing we want to do is to allocate the stack, and and we can always use the end of memory space as the stack pointer. And then you have to dedicate, you have to designate a register as your stack pointer. So whichever one you pick is fine. Out of the 4, you can designate A, B, C, or D as our stack pointer. I'm just going to pick D as our stack pointer. Okay. So I'm going to use comment here and specify use register D as our stack pointer. Okay. So we have to initialize the stack pointer first, and since the program is starting from location 0, it kind of makes sense to kind of use the end of memory space as the end of the stack. Is that okay? So we want to initialize the stack pointer. How do I initialize the stack pointer? We know it's LDI, but what do we put into register D as the location past the end of our memory space. Nope, it's a 0. Yep. Because the moment you subtract 1 from 0, what do you get? You get the largest integer in 8-bit in this case. So that's why we initialize D with a 0. So we initialize the stack pointer to be the past the end of the entire memory space. Okay. So that's all kind of done before main, so to speak. Okay. This is all done, in a regular C program, this is all done before main. So your actual main subroutine is actually after the initialization of the stack. All right, so now we need to call f. Okay, f is down here somewhere, which is just a label. So how do we call subroutine f? With the JMPI instruction, it's pretty easy to continue execution in f, which is not a problem, right? JMPI f, that will continue execution in subroutine f, or at label f, which is doing one part of calling a subroutine. But the other part is to say, hold on a second here. Once we are done with f, we have to come back and continue execution right after this instruction, right? That's the tricky part. How do we remember that? Well, we're going to use the stack, okay? So what we do is we specify continuation1, okay, as a label. It's a very long name, but it does indicate what it is for, okay? So before we do the branch, we have to remember continuation1 is where we want to continue execution after we execute the subroutine f. And out of the 3 things that we talked about, initialize, stack, push, and pop, what do we need to do at the cursor right here? Push. We need to remember that, right? So what we want to do is to say push continuation1 on the stack. But how do we do that? We don't really have a push instruction. And then we know that we're using register D. So what we can do is to go back to this slide here and say, okay, what is push doing? Push is going to subtract 1 from the stack pointer, which is our register D. And then we're going to store whatever we need to store into whatever the stack pointer is pointing to. Is that okay so far? Okay, so let's switch back here and say, what do? We need to subtract 1 from the stack pointer. Without sub I, which is subtract immediate, which is one of the things that we can do, once we can implement add I, we can do the subtract I. But without that instruction, what do we need to do? Yeah, it's going to be cumbersome, right? We need to LDI some register other than D. So let's say A with a 1, and then we say subtract A from D, okay? So this is basically the same thing as D equals D minus 1. Are we doing okay so far? So we are decrementing the stack pointer. And then the second thing we need to do is to store whatever we need to store onto the stack. Once again, we don't have a push instruction, or we don't have a way to directly store that. What do we need to do? LDIA with continuation1, okay? And then we use the store instruction, ST. This is the first time we use a store instruction. The store instruction is kind of like this, if I remember correctly. It stores whatever the second thing is to whatever the first thing points to. So we are storing register A to whatever register D is pointing to. Okay. Store continuation1 on stack. There we go. Then we can continue execution at F. F doesn't really do anything because it's empty in the C implementation. So the only thing it needs to do is to say, hey, I just need to go back. Where am I going back to? Okay. So once again, we have a stack operation here related to this instruction. Out of the 3, which one do you think is going to be? Initialize stack, push, or pop? We need a pop. We are retrieving whatever was stored on the stack earlier, which in this case is the continuation point. So we look into the pop operation in C, and then we say, okay, what do we need to do? we need to look at whatever the stack pointer, which is register D, is pointing to, put it into some space, and then we want to increase the stack pointer by 1. Okay, so let's go ahead and do all that. So the first thing we need to do is do LD, which is the opposite of ST, the store. So we need to, I'm going to use register A again. So it's exactly the opposite of what we did earlier. Okay, whatever the stack point is pointing to, I want to retrieve that byte from memory into register A. And then we need to adjust the stack pointer. Remember that we have to do that. The stack pointer has to be incremented by 1. So now we have to do a LDI, another register, say B with 1, and do an add instruction here to basically say, oops, D is D plus 1. Okay. Now that we have retrieved the continuation address into register A, what do we need to do to continue execution at continuation 1? Jump JMP without the I. JMP needs one thing. What should that be? Register A. There we go. But this is just implementing the first call to F. What do I need to do the second call to F? Pretty much the same thing. So we have 6 lines to copy, 6 YY, copy 6 lines, and then paste. And then one thing we have to change is to change continuation 1 to continuation 2. And also, oh, don't forget this one. If we change one without the other one, yeah, it's not going to work. Do you think this is going to work? Do we think that this program is going to simulate the calling to an empty subroutine F, go back, continue to call again, and go back again? We need one more thing before we can test this program. We need a halt instruction here because we need the whole program to stop. We don't really have a return 0. We don't have an operating system to return to. So the best thing we can do is to have a halt instruction to say that this is the end of the entire program. We don't have anything else to execute. Okay. All right. So we'll go ahead and give it a try. Okay. And the best way to do it is to use mousepad to look at sub.asm. So I can do a Control A, Control C, and then go to the spreadsheet to do a Control V. Assembler. To go back to another tab. Source, paste. There we go. No error messages. Good. This is one that I won't, hand enter all the bytes because it's quite a few, not too bad. Okay, so we'll go ahead and give it a try. So file, download as comma separated values, and we'll put it as sub1, which is the name that we chose for the C program. And then we go to Logisim, reset the whole thing, load from the temp folder sub1.csv. So now we have this program. How do we test to make sure that this program does work? You can use a log feature. Remember the log feature? So we go to simulate, go to logging. What do you think we should log to make sure this program works the way it's supposed to?
Register.
Which register do we want to?
A.
Register A? Okay, that kind of makes sense. Okay, so we can go to register bank and say, let's track register A. Register D is important, don't you think?
Yeah.
Because that's our stack pointer. We probably want to track the program counter, don't you think? Because that really is the one thing that tells us where are we executing, okay? Because everywhere we go, PC will leave a trail of where we have been, okay? So that's kind of important. Anything else? I don't think register A is going to be very useful to us, but we'll track it anyway. Anything else? Do you think we should track RAM? Because we are going to overwrite some portions of RAM with something and then retrieve it later on. So maybe that's useful. Okay, so we go to RAM. Which location do we want to track? Which one do you think is going to be changed? We initialize the stack pointer to be the very, very one byte past the end, which means the first push is going to be using which location? The very end. Okay, so we know that that location is going to be used if the program works correctly. So we want to track this one. Okay. Anything else? I think that should do it. Okay. So let's go ahead and just say that this is all we want to track, and we can run the simulator with ticks enabled, and it's clocking at 8 Hertz right now, which is pretty slow, which I think is okay. And we'll just enable it. Okay, you can see how it accessed the stack. Continue execution. And now it's stuck with the halt instruction. Okay, all right, so let's go ahead and stop the simulation and go into logging and see whether we are seeing what we should be expecting. Okay. All right, so register A is, it's not really that important, okay? This is register D, this is the program counter, this is RAM, and this is the RAM of the last byte of RAM, okay? So that's kind of important. We can see that register D is 0 to begin with, because that's because of the reset, and then we initialize it to 0, 2, okay, as if it is not 0 to begin with. When it became FF, that's because we are decrementing it by 1. Okay, and you can tell from the program counter which location we are talking about. This is location 5. So location 5 is most likely the sub instruction. How do we know whether location 5 is the sub instruction? Go to the spreadsheet, right? Go to the spreadsheet. You go to, there are a few places you can do it. You can go to the output, and you go to location 5, and this is a 6C0A. Actually, the subtraction instruction is probably the 04. Okay, let's go back to source. The line numbers do not change. The row numbers are preserved. So this is row 7. I think the first row is changed. Oh, this one is even better, because this one gives you a lot of busy information. But if you highlight a particular row, it would give you the location. This is location 4. So then you go back to the memory trace. Location 4 is right here, but the second doesn't seem to make any sense. This is location 4. When the program counter is at location 4, it's only when it's at location 5 that it changed to 1 FF. This is the time when it should be changed. But that's not what we are seeing. We see how register A got a 1. Oh, I know why. Because the program counter is already 1 step ahead. Okay. It creates a new row in the trace whenever something is changed. When is the program counter incremented? In the microcode, do you guys remember? The low up instruction has 2 slices. What does the first slice do? First slice is fetch, which means we go into memory, we grab the whatever PC is pointing to, put it into the instruction register. What is the second slice doing? It has 2 things to do, right? The first thing, one of the things that it does is to increment the program counter. So the program counter is incremented before the instruction even executes. So that makes sense now. Because by the time we see the effect of the subtraction, which is this one here, it is already incremented to 5, because this is the first slice, of grabbing the instruction. This is the second slice of the no-op instruction to decode it. By the time it is decoded, it is already incremented. This is when we actually execute the microcode corresponding to subtraction, and that's why we see register D decremented from 0 to 1. Okay. Now, I know we're running out of time. So the quick way to check whether this program works or not is to follow the program counter and see whether it goes to the location that we think it really should be going to. So we know that it should be going to, it should go to function f, which is at location 19. Nope, I take it back. It is at location 13. So let me just write it down on the whiteboard here. So we know that we need to call the subroutine. It should go to location 13 twice because the subroutine is called twice. We also know that right after it gets to location 13, right at this point, which is location 17, at location 17, the first time it has to go back to continuation 1. Continuation 1 is location 5. And then the second time it should go to continuation 2, which is location 18. Okay. So we should see these transitions. We should see that the program got to location 13 in hexadecimal, and then at location 17 it would go back to location 5, and then we'll go to location 13 again eventually after there are many instructions in between, and then after there are some instructions between these two, but from location 17 it should go to location 18. Is it 18? No, 12. Sorry, I'm looking at the wrong part. This is the decimal number. This is the hexadecimal number. So I should be looking at the hexadecimal number. So now we can go back to the simulator and see whether that is the case or not. So we only need to track PC in this case. What is 13 in binary? 00010011. Okay, so we want to look at that. This is the point. Okay, so we got to function f. This is proof that we got to function f. And at location 17, we should go back to location 5. What is 17 in hexadecimal in binary? How do we convert it? Okay, it's 1. This is 17, and then it got back to location 6. Oh, it's 6 because it is 1 past that point. Is that right?
It went to 18 as well, right?
Say again?
It went to 18 as well?
It went to 18.
Because it executes the next...
No, it never got to 1. No, it never got to 18, but the program counter gets incremented.
Right.
So that's why we see it incrementing to 18.
Yeah.
But we should see it go to location 5 because location 5 is where continuation 1 is. This is continuation 1, and it is supposed to be location 5. But I'm not seeing the program counter changing to 5. But we see it going to location 13 twice. This is the first time, and this is the second time. So it does work. It's just that at this point, I'm not sure how to explain why. Did it go back to location 12? This is location 12, so it did go back to location 12. It's just location 05 doesn't seem to be there. Because location 5 would be 0101, that's 5. This is location 6. No, this is location 10 already. Okay, am I missing something? This is right before the branch, which is location 7. Oh. This is location 7. which is this instruction here. From location 4, we are going to make the call. Oh, never mind. That's the use of continuation. So continuation is actually at 0A. I misread my own code. So continuation 1 is actually 0A, which is 1010, and then continuation 2 is 12, which is 0001. 0010. So I think we got that. Okay, so I think we got that because we got to location 0A. This is 0A, so the first return was successful. Then there's the second return should return to 12, which is this one here. So both returned successfully. I was just reading the assembly slide, assembly spreadsheet incorrectly. So it did work. So the evidence of the program does working is in the trace. Any questions about this part? Do you think this might be something that you have to do at work, 4 years down the line, you're actually working at the company? Do you think this might be something that you might be looking at? I'm not sure about you in your case, but this is what I was doing in 1990. Okay, the context is a little bit interesting because I was working with an embedded system company, and this is way before Arduino, or the new MCUs, became, available. So at the time, the hardware engineers would just drop a circuit board, on my lap, not literally on my desk, okay. And then say, okay, TAC, make this work. This is literally what they said to me, make it work, okay? So you'll be writing code, writing programs, and we had an assembler, and then you store the program in a ROM. We're not talking about Flash, ROM here. We're talking about ROM, which is, it has a little window, so you can use ultraviolet, light to erase the content. And then you have to erase it again after you program it once. Okay, it's not like you just write some code and it will erase. So anyway, you plug in the ROM after you program it, okay, and it doesn't work because all I wanted to do is to light up some LED after doing some work, and it doesn't get there. How do you debug a program like that? With a environment where you have a piece of hardware, you have the processor, you have the ROM, you have the RAM, and nothing else. How do you debug a program? How do you know that hardware people do not make a mistake and causing this whole thing not to work?
A lot of testing.
You need to do a lot of testing, but when you're doing testing, how do you debug your program? What does it have to do with this trace here? We have something called a logic analyzer. Okay, you can look it up. A logic analyzer is a piece of a machine. It has a gazillion, 50, 60 wires coming out of it. So what you do is you have these pods that will allow you to clamp the entire thing onto the processor itself. So what it does is it passively listens to the data bus, the address bus, which is kind of what we are doing here. So from the memory bus transactions, the logic analyzer has a special program to disassemble the program and say we're executing at this location, it is this instruction because it is architecture aware. So it knew that we were working with a Zilog Z180 processor. So from looking at the memory content, getting passed through the address bus, data bus, and all kinds of stuff like that, it can go back and reverse what kind of instructions we're executing, and then give you an idea of how the program worked or not worked in many cases.
Is that the processor you guys were making?
No, we were using only that processor, so we were just a consumer. That particular processor is the Zilog Z180 processor, which has a very rich history, because the predecessor of this processor is the Z80 processor, which was the processor used by CPM computers. CPM stands for control, I cannot remember. control program / master, if I remember correctly. So you can look it up, CPM. And of course, most people would go like, CPM, what do we care about CPM? Has no relevance whatsoever. Control program monitor, not master. If you watch Tron, the original movie, the bad guy, is called what?
Master something.
It's based on CPM, by the way. Yeah, it's based on the term CPM. And you might say that CPM is some really archaic processor that I have no interest whatsoever. It evolved into PC-DOS. Do you guys know that piece of history, of Bill Gates, trying to find? He promised IBM an operating system, okay? And what he did was not to write his own operating system. He was trying to use CPM as the operating, with some changes, it would run on the architecture that IBM was using. So he went to the guy who developed CPM to begin with, and the guy was out golfing, and then the wife answered the doorbell, and then Bill Gates had a suitcase of cash, like $50,000 or something. But it was a lot of money back then, okay? It was a lot of money back then. And then the wife said, no, go away. We are not interested. So Bill Gates never bought CPM from the guy who developed CPM. There was another guy who developed a clone of CPM. So Bill Gates found out who that was and went to this guy. The guy just took the suitcase and go like, okay, the program is yours. And then after that, that CPM clone eventually became PC-DOS. And then PC-DOS evolved into MS-DOS because Microsoft asked IBM, hey, can we change the contract? How do you want to change it? We want to reserve the right to sell this operating system under our own brand to whoever wants to buy it. IBM just go like, who would want to do that? Sure, we'll sign it off, no problem. And then after the IBM PC, the first personal computer, and also PC XT became available, what then happened? Compaq, okay, C-O-M-P-A-Q, okay, happened along with many other brands. What did they do? IBM clones. So people were no longer buying personal computers from IBM. They were buying these clones from Compaq and many other suppliers. So as a clone manufacturer, do you think you can approach IBM and say, hey, we make a clone of your computer, can you license your operating system so that we can use it too? No, IBM is going to say, no, we're not going to do that. So where did they go? Where did they turn to? Microsoft, because Microsoft says, hey, if you cannot get PC-DOS to run, we got MS-DOS, which is exactly the same thing. So that's how it started the whole thing, the whole PC market. Yeah, you guys can watch that movie. I think there's a movie made about this whole history of MS-DOS. So the next major step came along when Bill Gates went to PARC, P-A-R-C. What is PARC?
Outside Research Center.
Yes, and who owns PARC? PARC.
Xerox.
Xerox. So you go like, Xerox, what company is the Xerox? It's the copy machine company. Okay, so how does the Xerox have anything to do with the revolution of PCs? Well, as it turned out, Xerox is an East Coast company. Okay, and they hired a whole bunch of really bright engineers. And the engineers, they decided, hey, we want to do stuff, okay? And then Xerox only wanted to do copiers, right? So all of these engineers kept, bugging management. They go like, hey, boss, look, I got a really bright idea to do da 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 da. The boss go like, does it have anything to do with copiers? Not really, but I think it's better than copiers. We are not interested. So at some point, they set up a PARC, PARC, or the Palo Alto Research Center, as quote-unquote an asylum for these really bright people. Because they don't want to fire these bright people just in case they need them, but they don't want them to be bugging the management out in the East Coast either. So they set up PARC and go like, here's a playground, go play, go, 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 go. And these people developed the first GUI, the first mouse, the first GUI, and stuff like that. except nobody was interested. Xerox for sure was not interested, and there were no personal computers at the time either. So they had these computer clubs, locally around the Bay Area. Guess who were members of those clubs? Were in plural. Bill Gates and Steve Jobs. Exactly. So they both went to the park and witnessed, all these magical stuff because at the time it's brand new. Okay, if you move the device, you can see a pointer moving accordingly on screen. Whoa. You have to remember, these guys are used to text. Everything is like text, right? So they go like, oh, cool. Look, we can click too. If you press this button here, the computer can register that event and go like, hey, there's a click on screen. And then what happened after that? Well, you got Apple, the Macintosh, okay? Well, first there was the Lisa, which was a dismal failure. And then there was the Macintosh, which was successful, okay, with a GUI. And then on the other side, what do you get? Windows, exactly. So Windows and the original Mac OS, okay, started to exist after being inspired by these projects over at Park, okay? But that was not the, that wasn't the first time, that wasn't the last time that IBM and Microsoft had some dealing. What was the second time they had a deal?
Software.
Hmm?
Was it for software?
It's a software deal, yeah. But what was it? What came out of it? You guys use it on a daily basis. If you have a Windows laptop or desktop computer, you're using it daily. Windows, but it's not just Windows. Okay, let's look at the history of Windows. I know we're running out of time, but I think this is kind of cool. Okay, so we got Windows 3.1, which is the first popular version of Windows, and then we got Windows 98, 95, 98, 98 SE, which is the fixed version of 98. And then we got Windows ME, which nobody liked, right? And then what happened after Windows ME, Millennium? No. We got Windows XP, okay? The transition from Windows ME to Windows XP is significant because the core of that operating system just changed from MS-DOS to NT, to Windows NT. So Windows NT was the result of the second cooperation between Microsoft and IBM, the major cooperation. Okay, so both companies sent in people with a team to develop the next generation of operating systems. So Microsoft sent in some people, IBM sent in some people. IBM came up with OS/2, OS/2, which is IBM's version of the same thing, and then Microsoft came up with Windows NT, but they both had the same core, the same kernel. IBM could not really market OS/2 because OS/2 can only run OS/2 applications. It cannot run Windows applications. So I think it basically just died out in the end. And then Microsoft basically held on to Windows NT. So they had Windows NT as its own operating system until 4.5, if I remember correctly, and then it got into Windows XP. So we never call those NT anymore, but it's using the same technology. So that was the second and last time that IBM and Microsoft cooperated, in quotes. IBM got the best out of the deals both times. Okay, so there's a little bit of history that you guys might or might not be interested, but that's it. So what I'll do right now is I'm going to stop the lecture and I'll go to the lab. If you want to work on the practice test, I can answer questions in the lab. Yes, go ahead.
Just go over back to the mnemonics that we were,
Not this one?
No, I wanted to see what we put in the F, when we jumped to F in the microcode, not microcode, in the assembly.
So you don't want to go to the logic sim?
No, the spreadsheet that we, or the mouse pad document that we were writing.
Oh, okay. You mean this one?
Yeah. Thank you.
Yeah.
I wanted to see what you put down there under F. Okay.
Oh, okay, I see.
Thank you.
Mm-hmm. Yeah, so that's how you return from a subroutine. All right. Any questions before we transition to the lab? Questions? I'm going to stop the recording. and then we'll go to the lab. For those of you who want to kind of get a head start on the practice exam, we can talk about it at the lab.